Beneath the grid of streetlights and the constant hum of traffic, as millions sleep or rush to their destinations, an entirely different world awakens. It is a hidden city, a labyrinth of pipes, cables, and conduits that hums with unimaginable power and purpose. We walk over it every day, oblivious to the intricate machinery performing a silent, ceaseless ballet. Imagine a system so vast it can heat an entire district with steam generated miles away, or deliver light-speed information across continents through a strand thinner than a human hair. These are the veins and arteries of the modern city, invisible until they fail. Today, we delve into 4 of these subterranean networks, each an engineering marvel, each far stranger and more vital than you might expect. Number 4, the silent power grid beneath our feet. You plug in your phone, flip a light switch, or turn on your computer without a second thought. The power arrives, reliably, instantly. But consider the incredible journey that electricity takes from a power plant, sometimes hundreds of miles away, to your outlet. The most visible part of this journey is the towering lattice of transmission lines, those familiar pylons marching across the landscape. Yet, as these lines approach our most densely populated areas, they vanish. They plunge underground, not into simple residential wiring, but into a complex, high-stakes network of buried cables designed to carry immense power loads. The challenge of burying high-voltage electricity is not simple insulation. High-voltage alternating current generates significant heat, and unlike overhead lines cooled by the open air, underground cables are trapped in soil. Early attempts struggled with overheating and insulation breakdown, leading to spectacular and dangerous failures. The solution came through a combination of ingenious materials and structural design. Modern buried transmission lines, like those serving Manhattan, often use oil-filled or gas-insulated cables. These aren't just solid wires in a tube. Imagine a hollow conductor, sometimes filled with a highly refined mineral oil or even pressurized sulfur hexafluoride gas, a remarkably good electrical insulator. This fluid or gas not only prevents arcing between the conductor and the surrounding shield but also helps to dissipate heat away from the cable core. Some of the highest capacity cables are even cooled by circulating water through adjacent pipes to carry heat away more efficiently. Consider the 345 kV transmission lines buried deep beneath New York City. These are not just single cables, but often a trio of insulated conductors, each encased in its own protective pipe. These pipes, sometimes several feet in diameter, are backfilled with a thermal concrete to improve heat transfer to the surrounding earth. The sheer scale is staggering. Engineers must calculate the thermal resistivity of the local soil, the proximity of other heat-generating utilities, and even the ambient ground temperature to ensure these subterranean arteries don't overheat and fail. A single fault in a high-voltage underground cable can take weeks or even months to locate and repair, requiring specialized crews to excavate and meticulously splice connections that carry enough power to light up entire neighborhoods. It's a hidden, delicate ballet of physics and precise engineering, allowing our cities to hum with unseen energy. Number 3, the information superhighways of glass. The internet feels ethereal, a cloud of data floating invisibly around us. Yet, every email, every streamed video, every video call travels on physical infrastructure. For the vast majority of its journey, this data doesn't fly through the air, it pulses as light through incredibly thin strands of glass, fiber optic cables. And just like power lines, as these global networks reach our urban centers, they dive underground, forming a dense, intricate web beneath the streets. The principle behind fiber optics is total internal reflection. Imagine shining a flashlight beam into a long, thin tube of water. If the angle is just right, the light will bounce off the inside walls of the tube and follow its curve, rather than shining straight through. Fiber optic cables work similarly, but with microscopic precision. A hair-thin core of ultrapure glass, known as silicon dioxide, is surrounded by another layer of glass with a slightly different refractive index, the cladding. Light signals, generated by tiny lasers, are injected into the core. Because the cladding has a lower refractive index, the light hits the boundary between core and cladding at an angle that causes it to reflect inward, bouncing along the length of the fiber without escaping. These aren't just single strands. A typical fiber optic cable buried beneath a city street can contain hundreds or even thousands of these individual fibers, each capable of carrying trillions of bits of data per second. Think of the Maria subsea cable, stretching 4,000 miles across the Atlantic, carrying 200 terabits per second, enough bandwidth for 70 million HD video streams simultaneously. When this colossal capacity reaches the shores, it breaks down into smaller, yet still incredibly robust, underground cables that snake beneath our feet, connecting data centers, businesses, and eventually, our homes. These cables are protected by multiple layers of armor, sometimes steel or Kevlar, against accidental digging or even rodents. The greatest challenge for these networks in an urban environment is not capacity, but deployment. Navigating existing utility ducts, avoiding gas lines and sewer pipes, and ensuring future scalability requires meticulous planning and constant maintenance. The internet we access instantly is, in fact, an immense, intricate physical network, mostly made of glass and buried deep below us. Which of these hidden networks do you find the most surprising? Tell me in the comments below. Number 2, the invisible river that cools and heats our lives. Walk through many European cities, and you'll notice an absence of individual boilers or air conditioning units on buildings. Instead, entire districts are warmed in winter and cooled in summer by a colossal, shared infrastructure, district heating and cooling. This system operates through vast networks of insulated pipes carrying hot water or steam, and chilled water, often located kilometers beneath the surface. The core engineering principle is centralized production and distributed delivery. Instead of every building having its own furnace or chiller, a single, highly efficient plant generates the thermal energy. For heating, this often involves burning natural gas, biomass, or even utilizing waste heat from industrial processes or power generation. The heat is then transferred to water, which is pumped at high pressure and temperature, sometimes exceeding 100 degrees Celsius, through a closed loop of insulated pipes to various buildings. Once the heat is extracted by a heat exchanger in a building, the now cooler water returns to the plant to be reheated. Cooling works similarly, but with chilled water, often produced by large absorption chillers or electric compressors. Consider the Helsinki district heating network, one of the largest in the world. It serves over 90% of the city's heating demand, utilizing over 1,400 kilometers, that's roughly 870 miles, of underground pipes. These pipes are not simple PVC. They are typically pre-insulated steel pipes, often featuring an outer casing and a layer of polyurethane foam insulation to minimize heat loss. The challenge is immense, maintaining high temperatures over long distances, managing expansion and contraction from temperature fluctuations, and ensuring leak-free connections under significant pressure. The engineers correct a common false belief: many assume that individual building systems are always more efficient. However, central plants can achieve far greater efficiencies through economies of scale and the ability to utilize diverse, often renewable, energy sources that aren't practical for individual buildings. The trick is in optimizing the entire network, minimizing heat loss in the distribution, and matching supply to demand across an entire urban area, a testament to long-term urban planning and sophisticated fluid dynamics. Number 1, the subterranean labyrinths of waste. It is perhaps the most taken for granted, yet utterly essential, hidden network beneath our cities, the wastewater and stormwater systems. Every flush, every shower, every downpour on the pavement is channeled into a vast, complex, and often ancient, underground world that is literally fundamental to public health and urban function. Without it, cities as we know them would be uninhabitable. The engineering challenge is twofold: managing human waste and managing natural runoff. Early cities struggled with open sewers and street flooding, leading to epidemics and widespread disease. The solution began in the 19th century with the construction of dedicated, large-scale underground sewer systems. Modern wastewater systems primarily rely on gravity. Pipes are laid with a precise, slight gradient, allowing effluent to flow downhill towards treatment plants. The genius here is that this system often requires minimal external energy once the waste enters the network. Manholes provide access for maintenance and inspection, and pumping stations are strategically placed to lift wastewater over high points when gravity alone isn't sufficient. Storm water, the runoff from rain and snowmelt, is often handled by a separate system of storm drains, designed to prevent flooding by rapidly diverting water into rivers or other natural bodies. The problem arises when older cities have combined sewer systems, where stormwater and wastewater share the same pipes. During heavy rainfall, these combined sewers can overflow, discharging raw sewage directly into waterways, a major environmental and public health concern. The engineering solution for this, like in London's ambitious Thames Tideway Tunnel project, is to build massive, deep-level interceptor tunnels, essentially an enormous underground river designed to capture and store these overflow events until the treatment plants can handle the volume. Consider the scale. New York City's sewer system alone comprises over 11,000 kilometers, nearly 7,000 miles, of pipes, enough to stretch from New York to Beijing. These pipes range from small household connections to enormous interceptor tunnels several meters in diameter. The greatest engineering trick, often invisible, is the constant battle against blockages, corrosion from aggressive sewage, and the sheer hydraulic forces involved. Engineers must account for peak flows, designing systems that can handle sudden deluges, and the precise gradients to ensure flow velocity is high enough to prevent solids from settling but not so high as to cause excessive wear. This silent, subterranean network is a testament to the ingenuity required to support billions of lives, a constant battle against gravity and biology, ensuring our health and comfort with every flush and every raindrop. We are surrounded by impossible machines that somehow just work.